Okay, last time I talked about representations of SU2 or equivalently the Lie algebra SL2C. So we saw that start with the group G, which is SU2, say rho representation of G, finite dimensional. Then rho breaks up into direct sum y I in some finite set I, rho I irreducible, and we classified all. We proved that there exists exactly one representation one irreducible representation up to equivalence, of course, of dimension n there exists exactly one irreducible representation dimension n of irreducible representation and it breaks up into one dimensional eigenspaces under H. Recall the SL2C has a basis which I called EHF, H being this element, E being upper triangular nilpotent and F lower triangular nilpotent. And one had the bracket operations HE equals to E, HF equals minus 2F and EF equal to H. The Lie algebra of SU2 denoted SU2 is easily seen to be the set of the space of skew Hermitian matrices. And this H, the Lie algebra of the torus of a maximal torus in G in SU2 is identified with diagonal skew Hermitian matrices which are simply the with R times IH, I is the square root of minus 1 of this, then it's an irreducible representation, breaks up into eigenspaces for the torus and therefore also for for the action of the Lie algebra it breaks up into eigenspaces for H, eigenspaces under H, all the eigenvalues being integers R with minus n less than or equal to R being integers r with it's of dimension n, so I should say running from the integers r run from minus r to r. R running from minus being integers, let me say, how do I say this? The n-dimensional vector space, you start off with 2 by 2, so, being integers r running from minus n, right, okay, minus n by 2 to n by 2 if n is even, if n is even, and minus n plus 1 by 2 to n plus 1 by 2 if n is odd. Okay, there are 2n plus 1 numbers caught between these two and there are 2n numbers here caught between these two. Right, yeah. If n is even, runs from minus n by 2 to n by 2. Okay, so this is the, I might be making some mistake, it could be the other way around, I have to be careful. Okay, so this was one of the, that is, in other words, the rho h, eigenvalues of rho h are integral always, that is the statement. Okay, instead of h, if I want to, I can write this as saying if, see, the eigenvector for h is same as is an eigenvector for all of the whole one-dimensional vector space CH. So if R is an eigenvalue for H, then lambda R is an eigenvalue for lambda H. The reason I am making this first is the following. Now look at the three-dimensional representation. The three-dimensional representation is the adjoint representation. There is only one three-dimensional irreducible representation. Irreducible representation is the adjoint representation. And if I, so what happens is this, if you look at, say, any, well, what is it? Yeah, if I look at lambda h bracket with E is going to be 2 lambda E and lambda h f is 2 lambda. The upshot of this is the following. I'll denote by, let alpha denote the linear form, alpha from CH to C be the linear form alpha of H equal to 2. The eigenvalue of H in the adjoint representation is 2, you have this 2 minus 2 and 0 are the eigenvalues. So it's linear form alpha H equal to 2. Now, then for any eigen linear form in any representation rho, let me give it a name, any eigenlinear form lambda in any representation, lambda which goes from CH to C in any representation, we have lambda H by alpha H and any and let me write for any eigen form beta, let me call it, we have beta of lambda H by alpha of lambda H. Alpha is one specific eigen form occurring in the adjoint representation. If I look at this, it is in the beta H by alpha H, which is same thing as beta H by 2. And I know that beta H is an integer, so this is it says therefore that beta H is an integer for any. So what has happened is this, so twice this implies integer 2. This means twice beta lambda H by alpha lambda H is an integer. For every eigenlinear form on CH occurring in some representation. I will write here, instead of lambda H, I can put any non-zero element of CH. So let me write lambda of say U by alpha of U for any U in CH. Okay, so I am rewriting this deliberately in this form. 2 beta evaluated on any element of H divided by alpha evaluated on the same element of H is always an integer. So that specific element H, I can pick any element in CH and this ratio is going to be integral U not 0, so that it may make sense. Okay, why am I making this fuss? You will see presently. Now, I take G to be any compact semi-simple group and G is Lie algebra. Then we know that G tensor with C over R decomposes a direct sum of T tensor C T maximal torus compact connected. I always forget to say connected. T tensor C over R, which I will also denote. This also will denote GC this will be denoted TC. I also denote by H I times T. So that this T tensor C, TC is a C linear span of H as well as T. And then we know that GC decomposes as the sum of this TC plus sigma CE alpha, alpha and delta, a collection, a finite collection of characters on T, and for alpha and delta E alpha is an eigenvector for T corresponding to alpha. If now chi is any character on T, it will necessarily go into continuous homomorphism, so it will go necessarily into S1, the circle group, and this of course is contained in C cross. So then you find such a thing extends to a homomorphism, continuous homomorphism of, oh sorry, I don't want to say this. No. If you have such a thing, it induces, chi induces a linear map, again also denoted chi, of the Lie algebra of T, linear map chi of T in C, and that is the, whenever you have a homomorphism of the group into Lie algebra into the circle group, that is the corresponding Lie algebra homomorphism from the Lie algebra of T into Lie algebra of circle. Lie algebra of circle is nothing but, can be identified with the I times R, the imaginary axis in C. So you get a, that means, so you get chi, so let me for the present write chi dot, but I will later on induces a linear map chi dot, and you get the mapping chi to chi dot is a injection of the group xt of characters into home linear maps T coefficient into R. It will be IR, but makes no difference, I can call it R as well, or in other words into dual of T. So get the homomorphism, in fact get a injective map, injective homomorphism with xt onto home TR star, which can also be which itself is contained in home TC C. Strictly speaking, as I said, the tangent space to the circle is I times R, so let me put IR here, and that gets you into IR, but this contains this, but this can also be identified with home HR, because the linear form will take the character takes in chi takes values in elements. The chi of any element is a element of modulus 1. Correspondingly, the chi dot character takes from the Lie algebra takes into purely imaginary numbers, and therefore I times that, which is exactly h, takes everything into real numbers. So one has an actual identification of xt with home HR, and in fact this goes into this is a I, it's an isomorphism of xt onto a lattice XR. Lattice in H star. Lattice in the vector space. A lattice in the vector space is simply the Z module generated by a basis. You also recall that we choose the assume as we may. We have seen already that if alpha is in delta, minus alpha is in delta, we have a choice of elements E alpha in the eigenspace. This eigenspace denoted G alpha. We have choice of elements E alpha and G alpha not equal to 0, and therefore we know that the G alpha are one dimensional, so G alpha are actually C times E alpha. The choice of elements G alpha and G alphas, alpha and delta, such that the Killing form pairs these two to give you the value 1. Of course, we also have Bg E alpha E beta is 0 if alpha plus beta is not 0. And also Bg of H E alpha is 0 for every alpha and delta. So this in particular means that this Bg is the Killing form. When you restrict to H, it becomes non-degenerate. We know that the Killing form for semi-simple Lie algebra is non-degenerate, and these have already been paired. If you look at the subspace generated by sigma C E alpha, alpha and delta, here the Killing form is already non-degenerate because E alpha and E minus alpha give you 1 and the others are all orthogonal to each other. So on this the space is the Killing form is non-degenerate, therefore it is also non-degenerate on its orthogonal complement, which is precisely this. H is the orthogonal complement of this sum C alpha because H is 0 is orthogonal to every E alpha, and the entire Lie algebra is spanned by the E alphas and together with H. Because of that, you find that so Bg restricted to H, Bg restricted to this, as well as Bg restricted to H are non-degenerate. Now, we also saw last time that if I look at the group for alpha and delta, I denoted by T alpha is the kernel of the character alpha going from T to S1, or rather let me first call this T alpha prime, and T alpha is the identity connected component of T alpha prime. The connected component is the identity. This is a torus, and alpha is a non-trivial character of codimension 1 in T. And I will look at the centralizer of T alpha, again the connected component of the identity connected component of centralizer of T alpha, call that ZT alpha. Then this is, we know that ZT alpha is the almost direct product of the commutator subgroup and T alpha. G is T alpha this commutator subgroup I will call G alpha. Notice that this is equal to G minus alpha, because T alpha is same as, what I call T alpha is same as T minus alpha. The kernel of alpha and alpha inverse are the same. Okay, so, and what is, I claim that the Lie algebra of G alpha I claim of G alpha, which I call Gothic G alpha, is precisely C E alpha plus C E minus alpha plus C H alpha, where H alpha is bracket E alpha E minus alpha. Remember that we chose this E alpha such that their under the Killing form their product is 1. That is how E alpha E minus alpha are chosen, and with that choice of H alpha you see E alpha E minus alpha C H alpha. Now see, this is the basis E alpha E minus alpha H alpha is almost like the basis E F and H, except that we cannot guarantee that when I take the bracket of H alpha and E alpha, I cannot guarantee it's twice E alpha. It should be some multiple of, some multiple of E alpha. So you have, what you find is this, H alpha E alpha will be equal to alpha H alpha E alpha and H alpha E minus alpha equal to minus alpha H alpha E minus alpha, except for the fact that this alpha H alpha is not 2, it is very similar to the basis which we already have. Now that can be corrected by replacing H alpha by a suitable multiple of H alpha and may ensure that the two are 2. So the algebra becomes isomorphic to our standard algebra E, H and F, because the bracket operations will be what you get out of that. Okay, now the point is that, so we have a basis of G alpha through its identification with SL2C. Now, so this we have a
H alpha is so chosen so that it is SL2. That the values are 2.
no, as things stand, it's not quite SL2. I have to be careful. I have to modify H. If I want 2, I have to modify H. If I modify H, things will work out. That's what I'm saying.
But you don't want to assume having modified so that it is becoming 2 now?
Not yet. Do that. No, because you see, the whole thing is tailored to the killing form. So I don't want to modify the basis to suit that. But I'll tell you why I am doing this. So what I find is this. So hence the other basis, through its identification with have another basis which I'll call, I'll give it a name. So E prime, so let me call it E alpha, H alpha, F alpha, where these things become multiples of corresponding E capital letters, capital E alpha, each. So what happens is H alpha will be a multiple of H alpha. Now this implies immediately the following. For every beta in delta, 2 beta H alpha by alpha H alpha is in Z. This is exactly what I did in the case of SL2. The fuss I made about choosing instead of H a multiple of H and so on. This is the reason why I want to. So if you like, this ratio is an integer, 2 beta H alpha. Notice alpha H alpha in particular is not 0. After all, H alpha is a multiple of this H, is a non-zero multiple. Non-zero multiple of H, and therefore this 2 beta H alpha is non-zero. This is going to be an integer. Sorry, not non-zero multiple. So this can be 0, beta can be 0, but alpha H alpha cannot be 0, won't be 0 because we know that alpha H is 2 and it's a non-zero multiple, so this is not going to be 0. In fact, we will see presently, in fact, alpha H alpha, it turns out, is greater than, is always positive. We will see.
Is the alpha little h alpha, capital H alpha?
Sorry?
The denominator, little h alpha, capital
It doesn't matter because they are, but it will cancel out. That's the calculation we did.
See, H alpha is a multiple of small h alpha.
So it doesn't.
If I put both small h alpha here, it's clearly integer, but both are multiples of non-zero multiples. So you are in good shape.
It cancels out, right? It cancels out.
Sorry?
It cancels out.
It cancels out, yeah, right. Okay, so this is one of the crucial facts about delta, about this set of roots. Delta is called I have already told you, delta is set of roots in set of roots of G with respect to TC. And we also saw last time, and I will repeat it now, the following statement, that is okay, lemma if you like. The inner product of
here beta is the root for the capital G, right?
For capital G, yeah.
Sorry?
Beta is the one of the roots for the capital G we started with.
Capital?
G, the group.
Yes.
G.
Yeah, set of roots is, I will freely go between the group and the Lie algebra.
But we have
No, what, no, the point is, this is an SL2 and beta is a eigen character for SL2 in some representation, in the adjoint representation. And I have shown that for any representation, whatever eigen character you take, the ratio is an integer. Okay? I am using it only for SL2. I am getting the result for any pair of roots beta 2 beta alpha by alpha h alpha. I find this an integer. I look at the group. That's why I look at this group, the SU2 corresponding to this group, and you have the adjoint representation. You can restrict it to SU2. You get a representation SU2, and what are all the characters occurring there? Which are the characters occurring in the representative called weights. All the weights are precisely the roots. The weights restricted to the beta restricted to the various to the torus are the roots, and therefore they are weights for the representation.
Simply alpha h alpha is 2, so 2 by 2 is 1, and beta h alpha he has proved is an integer. That's all.
No, he was more worried about this statement being in Z is a statement about SL2.
Yeah.
That's all.
Yes,
That's the point. That's the point he was raising.
Yes,
Yeah.
it's a statement about SL2.
It's a statement about SL2.
Yeah. Alpha h alpha is 2, 2 by 2 is 1.
Notice that this implies also, I mean, you can interchange the roles of alpha and beta, because this was proved for any root alpha. You could have interchanged the roots, so you also find 2 beta, 2 alpha h beta by beta h beta is also in Z. That's also true. Because I can interchange the roles of alpha and beta. Alpha is any root, so I could have started off with beta and done the same thing. Okay, so the lemma we proved last time. Let me, the killing form h alpha h beta applied to h alpha h beta is nothing but yeah, it's alpha of h beta, which is also equal to beta of h alpha. Why is this? This is because of the definition for h alpha and h beta. So you took the inner product of h alpha and h beta, that is Bg of h alpha h beta is what we are interested in, but by definition this is Bg of, let's write, h alpha and the bracket of E beta, E minus beta. And now the killing form is invariant under the adjoint action of the Lie algebra. So this equals, because of that, Bg of take this over to this side, you are going to get minus of h alpha E minus beta comma E beta, but this is minus Bg h alpha E minus beta is minus beta of h alpha, which is same thing as beta h alpha. The minus sign is the course, there is a minus sign here, E minus beta E beta, but E minus E beta is 1 we know, so this is nothing but beta of h alpha. So that's h alpha h beta. Interchanging roles of alpha and beta, you can prove it the other way around. So you find that that's the lemma Bg of h alpha h beta is alpha h beta equal to beta h alpha. Sorry?
So wouldn't this follow just by interchanging roles of alpha and beta? Wouldn't this follow?
See, if something being invariant under Lie algebra means this. In general, if you have B xy on the Lie algebra is a invariant form, means the following: for every z in G, B of zx y plus B of x z y is 0. Something being invariant in the group, you understand, and then you take the derivatives, then you will get this statement. Applying Leibniz formula, you will get this. So this is what invariance means. I am using that invariance here. Where is it? I wrote.
On the left.
Yeah.
On the left.
Here.
On the left side.
Huh?
This side.
Yeah. Oh yeah, here. Instead of taking the bracket, here I took the bracket of z here, but then instead of that I look upon this as E minus beta E beta, and that shifts to E minus beta H alpha with a minus sign. So that's what happens. Okay, so Bg H alpha H beta equals alpha H beta.
H alpha and H beta are not canonical.
Sorry?
I mean,
No.
one needs to
No, they are wants to. I'm doing everything with the killing form. It's canonical, therefore. Because if I change E alpha by lambda E alpha, E minus alpha will have to be changed by lambda inverse because you want the inner product to be 1. I chose E alpha and E minus alpha as the inner product, not inner product, the bilinear product defined by the killing form should be equal to 1. Once you choose the E alpha E minus alpha in such a way that the inner product is 1, H alpha is uniquely determined. And no matter how you choose E alpha, once you choose E minus alpha so that the inner product is 1, the bracket is going to be the same. One gets multiplied with lambda, the other gets multiplied with lambda inverse when you change.
SL2 triple.
Huh?
And this is also an SL2 triple in the sense that you talked about. It is SL2 triple.
SL2 triple?
Meaning
Yeah.
it has the correct bracket.
Well, no, not quite, because you can't be sure that alpha H alpha will be 1.
Right. So there is some.
Now you have to modify if you want the SL2 basis there, you have to be a little more careful. You have to replace it by essentially 2H alpha by the H alpha H alpha. If you replace H alpha by then things will work out. Then it becomes, see, on this alpha is 1, alpha is 2 on this, and minus alpha is minus 2 on that. Then things work out right.
This is what is called the code.
And you have to also modify. So if you want this element to be the bracket, you have to modify E alpha and E minus alpha also. One of them you have to modify. E alpha, E minus alpha. You see, if the inner product is 1 in the killing form of SL2, things are okay. But what I have done is to make the inner product to be 1 in the killing form of the ambient group. The killing form of the ambient group, when you restrict to the SL2, is a multiple. So it depends on what that multiple is. That's how you have changed things. Okay. But this choice of E alpha, of H alpha is canonical. What I have defined as H alpha comes out of the killing form automatically.
Everything is canonical. E alpha, everything is canonical.
No, E alpha is not.
E alpha is not.
E alpha is defined only up to a multiple. Once you choose E alpha, E minus alpha is chosen. Once E alpha is chosen, the pair E alpha E minus alpha has to have inner product 1. That doesn't fix the pair. If you can modify one by multiple, the other gets multiplied by lambda inverse. So that's what happens. But the H alpha is well defined. It's independent of the choice of E alpha you made. Provided the inner product E alpha E minus alpha is 1, H alpha is fine. Now, so what did I want to say? Yeah, the other thing I want to say is the following. Restricted to H is positive definite. We know that the killing form of the compact Lie algebra is negative definite. So on I times the compact Lie algebra, the killing form is going to be positive definite, and our H is contained in I times the compact Lie algebra. because for every element in the compact Lie algebra, all the eigenvalues are negative, I mean are purely imaginary. So because of that it becomes negative definite, and therefore I times that everything becomes positive definite. So in any case we already seen it's non-degenerate. So for you have get the non-degenerate pairing, PG restricted to H, it's actually a positive definite pairing, gives an isomorphism of H on its dual. Real dual. It's a real vector space, gives an isomorphism, and the claim is the following, and hence since the killing form is positive definite on this, hence get a positive definite form on H star. We will denote these positive definite forms on H and H star by this. This is inner product, so I will denote it like that. So whenever a vector space with inner product, the dual also acquires the inner product, and that's exactly what's happening here. H and H star have naturally identifiable inner product. So once you fix the inner product on one, automatically you get one or the other. And then if you have a linear form, suppose you have a linear form, it gets identified with some element for any linear form. Lambda on H, there exists H lambda such that lambda of H equals H lambda H for every H in H. If you take a linear form, then there is a unique element H lambda such that H lambda H is equal to lambda H for this linear form. It's a standard linear algebra. And what happens is this, and the notation H alpha was chosen with this in mind. What I called H alpha is nothing but we already proved this statement. H alpha H is alpha H. I proved it for H beta that this is true. Alpha of H beta is H alpha H beta is what I proved, but the proof, if you look at it, goes through verbatim with any, instead of H beta you plug in H there. The inner product of H and E alpha E minus alpha you take, then you will get this. Okay, we saw that twice alpha H beta by beta H beta is an integer, and we also know that beta H beta is actually positive, because we know if H beta is non-zero, beta H beta is positive because the form is positive definite. Beta H beta would be H beta H beta, which is positive. We know that this is a ring. Yeah. Now this can be written as twice H alpha H beta by beta H beta. This is in Z, and then I can multiply this by So, this product is in Z. What is this product? I say this is nothing but cos theta, where theta alpha beta is the angle between, cos square is the angle between H alpha and H beta. Standard formula which we know, the angle between two vectors, if you look at, you take the inner product of the two vectors, cos theta is nothing but the inner product of the two vectors divided by product of the norms of the vectors. Square that, you get this business. And this tells you something. See, this number is less than 1, less than or equal to 1. So, this product is less than or equal to 1, which means each of them independently. So, sorry, this is the 4 cos square theta, 4 cos square theta. So, this product is less than 1, which means each individual factor must be less than or equal to 4. And equality can occur only if these two numbers are both 2, both are 2. And that can happen, the angle between the two will have to be 0, only then that can happen. And so, that means H alpha is a multiple of H beta, which cannot happen unless beta is minus alpha. We have seen that also. That means if alpha beta are distinct roots, you have strict inequality less than 4 here. Alpha not equal to plus minus beta, MI if you like, implies two is strictly less than or equal to 3. It's also true of 2 beta H alpha. Yeah. So, the only possibilities are this are equal to this, otherwise these are equal to plus minus 1, or 0 is a possibility, plus minus 1. 0 is a situation when the two vectors are at right angles to each other. These are the only possibilities. So, the set of roots is very limited in many ways. This one constraint you have it on them. So, you find, so that's another lemma, if you like. Yeah. So, all of which I should have stated as a lemma.
So, why do we want to multiply by the second term?
Sorry?
Why do we want to multiply by the second term?
See,
What is the...
no, only if I do that I am going to get cos square. If I take this ratio and divide it by norm of beta times norm of alpha, that is when I get cosine. And these are norm squares, both these. And you want the numerator also squared. So, okay, now, so that also I should state as a lemma, which is for future use. Two alpha beta by beta beta equals plus minus 1 or plus minus 2 plus minus 3 if alpha not equal to plus minus beta. When it is equal to plus minus you get 2, I mean you get 4, 2 alpha beta by beta beta. If I take alpha here, 2 alpha beta by beta beta, a square, the square is, oh sorry, it should be, yeah, if I take the square of this, when you take this also as alpha alpha, then you find you get 4. So if we take minus alpha, also alpha minus alpha, alpha alpha and minus alpha, that will be minus 4. Those are the possibilities. If alpha is not equal to plus minus beta, this is true. There is one other thing that's happening, which is interesting. Now if you look at the, you have the group G, and then if you fix a root alpha and delta, get the subalgebra E alpha, E minus alpha, C E alpha that corresponds to an SL2C, and correspondingly get a subgroup of G which is isomorphic to SU2 or SO3. I look at that complex subgroup, and it's, you can easily see that it is stable under the action of the Galois group. If I look at the C, the Galois group of complex numbers or real numbers, so it's simply it's a group of order 2 conjugation, you find that this space is stable under the conjugation. So if you look at the fixed points under the conjugation, I get a real subalgebra, and the conjugation came from the originally treating the Lie algebra of G as a real Lie group, real Lie algebra, and that's how, and tensor with C, and that's how the conjugation came. So when I take a subspace which is stable under a subspace of GC which is stable under the conjugation, then we will get a subspace of the Lie algebra of G. So this, that's how, and the corresponding subgroup is either SU2 or SU3, because it's a 3-dimensional group, it's got to be SU2 or SU3. Now, and let's look at in SU2, also sits in SL2C if you like. Now, SU2, you have the T, the maximal torus. Let me write D, diagonals in SU2. Which is, huh?
In the lemma you forgot 0.
What is 0?
In the lemma you forgot 0.
Oh, 0, yeah, sorry. Can be 0. We'll see with examples that 0 can occur. D diagonals in SU2. Now, in SU2, what is the normalizer diagonals? So you have this group SU2, and if you look at, you are looking at the diagonals, under the diagonals, the vector space C2 breaks up into 2 eigenspaces under diagonals. The diagonals consist of things like e power I theta, e power minus I theta, and you have an eigenspace corresponding to this e power I theta and another corresponding to e power minus I theta. So space breaks up into this. And now if I take anything in normalizer, any element in normalizer torus, normalizer diagonals, it has to permute the eigenspaces. If it normalizes the diagonals and you have eigenspaces are diagonals, anything in normalizer must permute the eigenspaces. And so the only permutation which you can get out of this, there are only two eigenspaces, the permutation is the group of order 2, and you can get the permutation group does that, but the permutation group is not in SU2 because it is of determinant -1. So, modify it by -1. This element I may call it W. It is an element, and if you have anything in normalizer, it permutes permutes eigenspaces. So it's either keeps each eigenspace in itself or switches the two. So there are only two elements modulo the torus itself. The Weyl group of SU2 is of order 2, and it is generated by this element W. I am going modulo the torus. The Weyl group is normalizer of the torus modulo the torus. By definition, the Weyl group is normally the torus modulo the torus, and those elements in the normalizer which keep both eigenvectors, each eigenspace fixed, that is precisely the torus itself. It means T fixes one eigenspace as well as the other eigenspace. The element fixes one eigenspace as well as the other eigenspace, which means it's diagonal. So it's a torus. So if I go modulo the torus, I am going to get, it's a element of the group I get is a group of order 2. So if you like, this is the Weyl group. So if I now, I will call the element, maybe I will call the element not W but S. And if I am working with this particular issue to correspond to the group alpha, the element of the Weyl group with respect to the torus in G alpha, which is like T intersection G alpha connected component. This is an element of order 2 denoted S alpha. Now the Weyl group permutes the roots, because the Weyl group is something which is in the normal Weyl group of the group G is normal of the torus. It permutes therefore the eigenspace of the non-trivial eigenspace of the torus acting on the algebra, and therefore it permutes the roots. The Weyl group permutes the roots. And this element S alpha, notice S alpha is in G alpha, which is in turn is contained in Z of T alpha. And S alpha on T alpha, S alpha acts trivially on T alpha because it belongs to ZT alpha. Everything is ZT alpha, so ZT alpha is center of T alpha. So S alpha being in ZT alpha implies S alpha acts trivially on T alpha. Or taking Lie algebras, you find that S alpha, add S alpha if you like, stabilizes T alpha and stabilizes T and acts trivially on T alpha, the Lie algebra of T alpha. So what has happened to the, and S alpha preserves the group preserves the Killing form, therefore S alpha preserves the Killing form, and therefore its restriction to the Lie algebra of T. On the restriction of Lie algebra of T, we know it's negative definite. What S alpha does is to fix a codimension 1 subspace pointwise. It fixes T alpha pointwise, and therefore it is nothing but reflection in that plane. With alpha equals 0. So what happens is this. This is T alpha. This is nothing but V in T alpha dot V. I mean, I will use both alpha dot and alpha interchangeably. Sometimes I will say alpha, which means the corresponding linear form corresponding to the character, but I also denote by alpha dot. V into alpha dot, this is T alpha. So it fixes a codimension 1 subspace and takes every vector orthogonal to it into its negative. That's what's happening. It's a mirror reflection. Okay. So this. So if you look at NT acts on T, and hence also an H acts on NT, and S alpha, S alpha is in NT because it is in ZT alpha, therefore it certainly centralizes T alpha, and then it normalizes the diagonals, which is the extra piece in the torus. So S alpha is already in G. S alpha is also, so S alpha actually normalizes D times T alpha, which is the torus. D is the diagonals in SU2, which we know S alpha normalizes, and this therefore it normalizes T alpha. In fact, it centralizes T alpha, therefore it normalizes this. So S alpha is gives an element in the Weyl group. S alpha gives an element in WG is NT by T. So you find that NT acts on T, and you have got this element S alpha sitting there, and the action on T acts trivially. So get NT by T into GL of T. You get a natural map from linear automorphisms from NT by T into GLR by T. You get a representation, so to speak. But this is W, the Weyl group. I will now just write W instead of WG. So the Weyl group acts on this, and what is more, it acts faithfully, because if you take an element in WG which is not in T, then its action on T is non-trivial, therefore on the Lie algebra it is non-trivial, so it's a faithful representation. So you get a faithful representation of W on T or for that matter H. And in this representation, every S alpha acts as a reflection with respect to suitable hyperplane T alpha. And what is more, with respect to dipole, I can equivalently say it's the same thing as acting on the dual of T alpha, dual of T. Yes. With W acts on T means it also acts on this. It also acts on the dual. Okay. I mean the T and the dual have been identified in any case because of the inner product, which we know is. So, or H for that matter. So, this yeah, one of the basic results which I will not be proving today but will prove later is the following. The W is generated by S alpha, alpha and delta. The Weyl group is a group generated by reflections. It's a finite group. Why? Because NT by T we know is finite. It's a finite group generated by reflections. And finite group generated by reflections have all been classified. They are called what? They are known as what are called Coxeter groups. This is the theorem which I will not prove, but let me state it all the same. There is a subset phi and delta such that W comma pi GS S a subset of G is a Coxeter system if the following holds. One, if sigma is in S, sigma square is 1. Two, if you let P(s) prime be the minimal integer, such that SS prime power PSS prime over here equal to 1. We allow PSS, we will say that that is, let me PSS prime is the, let me put it like this, is the order of S times S prime, be the order of this. Then we also assume that sigma square is 1 and sigma not equal to sigma prime. I mean, they are distinct elements, sigma and S, they are distinct elements, sigma, so this is okay. So PSS prime be the order of then G equals the free group on S modulo the system of relations, the normal subgroup generated by S square S in S and SS prime power PSS prime. When I say the order can be infinite, S square S in S, SS prime PSS prime, take the subgroup generated by this union SS prime, normal subgroup generated by this, SS prime in S, both are in S, take this normal subgroup. Then G is isomorphic to the free group on S, modulo the relations, S square is identity and SS prime per PSS prime is also identity. So generators and relations are given to you. If you have that, you call it a Coxeter system, and G itself is called a Coxeter group. G may have several Coxeter systems. I mean, G may be associated with the same group, may have several Coxeter systems on it. That is, the S choice is not unique. There are several possible S. Such a thing is called a Coxeter system, and the group G itself is called a Coxeter group. So it turns out a
unique up to conjugacy.
Unique up to conjugacy, yes, right. Right.
Sorry? So there, it may not even be unique up to conjugacy. Like dihedral groups, they could be smaller dihedral groups cross Z by 2Z, which will give you something like an irreducible Coxeter system, whereas it can also be considered as a dihedral group itself, which will be reducible. You may even have different cardinalities of S.
Maybe, I'm not sure, okay. I'm not able to think now, not comment on that. So his S is need not be unique up to conjugacy. Yeah, you see, the point is if there are outer automorphisms which are not inner of the group, then in fact, if you take the Dinkin diagram and interchange the first of A and interchange the roots outside.
But they take S.
Huh? It's not doesn't come from inner conjugation. So you're right. Yes, it need not be.
In fact, S can have different cardinalities.
Sorry?
The set S
Yeah.
may even have different cardinalities.
That I'm not sure.
Dihedral groups one can think about. You can have a dihedral group of order 100, which is the cross product of two smaller Coxeter groups, dihedral group of order 50 and Z by 2Z.
It's not product.
Okay.
The center, the Z by 2Z can be chosen to be center. Let's think about it.
Yeah, okay. I'm not. All uniqueness statements are withdrawn. Okay, but this is the definition of Coxeter group, and this has been extensively studied.
And classified. And they are classified.
They have been classified, yes. The groups. No, well, they have been. I don't know up to what point. I don't know if hyperbolic Coxeter groups have been completely classified. I'm not sure. Maybe they are. Maybe they are.
For affine Weyl groups. So they
No. The affine Weyl groups are not hyperbolic Coxeter groups.
No, but these are Coxeter groups in this sense.
No, there are Coxeter groups that occur as isometric groups of constant curvature spaces.
That also. But I am saying that another example of a Coxeter group is affine Weyl group.
Right.
So they are certainly there.
Yeah.
So there are two more.
When the Weyl group is finite,
Yeah.
they have certainly been classified, and the affine situation is also classified, which is. Sorry.
Is there any intuition for the definition?
What for the definition?
Intuition. What is the
Is there any intuition behind the definition, or
Well, the point is this. It's the thing is when you studied the finite groups of generated by reflections, it turns out that they have this presentation. That's what Coxeter proved, and that's the reason that these things are named after him, Coxeter. I can tell you one amusing incident. Coxeter essentially worked on Euclidean geometry, but from a higher standpoint. It's not. He went well beyond our normal Euclid geometry and so on. He was handling many dimensions and so on. On one occasion, I was visiting at Columbia University, and he came to give a colloquium there. And these reflection groups figure prominently in the context of Platonic solids. They're all stable under all kinds of reflections, and the group general reflections act transitively on them and so on. And a graduate student, he came to give a colloquium talk, and a graduate student had prepared a cake in the shape of a dodecahedron for the occasion, because he did lots of things with those objects at the university. So Coxeter is a Canadian mathematician. Well, I think my time is up, so I'll stop here. A couple of minutes left, but